So we're now going to move on to our third and final talk of this session. So Natasha Senior, she did her PhD in mathematics here at UEA on jet formation in barotropic turbulence.
That's right.
And she has recently joined CRU as a senior research associate. Unfortunately, she can't be here in person this afternoon, but by the power of technology, she has now appeared on our screen. So Natasha's going to talk about extreme precipitation triggered by equatorial waves in the Maritime Continent. Over to you, Natasha. Thank you.
Thank you, Tim. I'm here to talk to you about the work I've been doing on the 4C project at CRU on precipitation extremes triggered by equatorial waves. So this is the Maritime Continent. It's an area of the tropics that experiences deep convection that fuels the global atmospheric circulation. But because of this, extreme rainfall is one of the major forms of high impact weather experienced by the region. So for example, floods have comprised 30% of natural disasters in Indonesia. So it's very important that we're able to accurately forecast the precipitation, which requires the use of high resolution models to be able to faithfully capture the convective processes, which are parameterized in low resolution models. So what I'm here to talk to you about is equatorial waves and how they might organize convective systems and correlate with high impact weather events and provide a source of predictability. So I'm going to primarily focus on Kelvin waves in this talk, but I'll also touch on Rossby waves. So this is the image on the left here is a equatorial Kelvin wave. This is a theoretical structure. The shading here is the convergence, i.e. the negative divergence. The vectors over here are the horizontal wind vectors. And as you can see, for a equatorial Kelvin wave, there's a center of convergence that sits directly on the equator. And this is the region where we'd expect there to be convective activity, precipitation, and the convergence. You can see from the two converging winds that this region will bring together. The winds will converge over here and may trigger the release of available potential energy, which will lead to the convection and the precipitation. This whole structure moves eastward. It's got an eastward face speed as well. So equatorial Rossby waves, so this image now on the right, are a little more complicated. They have off-equatorial regions of convergence. So we'd expect if a Rossby wave is passing, an equatorial Rossby wave is passing over, then the region of precipitation we'd expect would sit maybe 5 to 10 degrees north or south of the Rossby waves passing over the equator. And this one has a westward face speed, so this whole structure will move to the west. So in order to study convectively coupled Kelvin waves, we're going to have a look at Padang, Sumatra. So Sumatra is an island on the west of Indonesia, and adjacent to this is the Indian Ocean. So just off to the west here is the Indian Ocean. So a convectively coupled Kelvin wave that forms in the Indian Ocean will travel towards the east and will impact Padang and may bring high impact weather with it. Since Padang is an equatorial city, this is a good case study city to examine this. Also important for the convective processes is the Bukit Barisan Mountains, which runs from the northwest to the southeast of Sumatra, so just along the coast as well. So this could provide an additional orographic uplift, which enhances the convective processes. We're going to define extreme precipitation here as the days in which the daily total precipitation exceeds the 95th percentile. So at Padang, this corresponds to greater than 32 millimeters of rainfall a day. So examining a database of CCKWs that we've created, we find that there's 64 CCKWs that coincided with extreme precipitation days between 1998 and 2020, which corresponds to a 55% increase in chance of observing extreme precipitation given the presence of a CCKW. So to try and understand how this gives rise to extreme, how these waves give rise to extreme precipitation, we're going to examine some composites comparing days in which there's been extreme rainfall without a CCKW present and when there is a CCKW present. So this is a Hofmüller diagram, which we're going to look at. So we've got longitude along the x-axis, time along the y, and this has been latitude averaged. So we're essentially looking at the latitude mean behavior of the precipitation. So yeah, the shading here is the precipitation rate. And also as you go up, the direction, that's the direction of time. So as you go up, we're looking further and further along time. And also the units of time over here are lagged from UTC 0-100 hours of the day of extreme precipitation. So this is a composite. So all of the extreme rainfall days in which there's no CCKW present in the data set have been lagged from UTC 0-100 hours. So this figure is the extreme rainfall when there's no CCKW present. So if we have a look at the day of extreme precipitation at lag 0, you can see that I've marked on this precipitation envelope. The precipitation peaks at Padang in the evening and propagates offshore overnight. And this follows these tongues of anomalous easterlies. So these red contours over here are the 10-meter zonal winds. This is the overnight land breeze, which arises from the fact that during the night, the land cools faster than the sea, which gives rise to this circulation on the surface. So the front associated with this propagation is convectively active, and the convection propagates offshore overnight. And this is the diurnal cycle of precipitation. You can see that the difference between the extreme precipitation day and the day before is simply that the precipitation on the extreme precipitation day is stronger. This follows the pattern of the diurnal cycle that we expect from these islands in the Maritime Continent. So when a CCKW is present, this picture changes. So if we look at minus 24 hours, we can already see that the CCKW is approaching. You can see this in the convective activity. I've marked on this green envelope to sort of show the general trajectory of the CCKW. You can see it's coming from the west, and it comes in, brings this convection, amplifies the offshore convection from the diurnal cycle the day before. So we get this huge amount of offshore precipitation. And then on the day of extreme precipitation, so having a look over here, you see that the peak precipitation just occurs before 12 UTC, which is earlier on in the day. Usually in the diurnal cycle, we get this evening precipitation, but this is occurring earlier on in the afternoon. So also one thing to note is that most of the CCKWs that we looked at arrived in phase with the diurnal cycle during the 12-hour period where the diurnal cycle is convectively active. So it seems that these are most likely to trigger extreme rainfall. Another feature to note is that the convective envelope of the diurnal cycle that's been interacting with the CCKW doesn't propagate that much offshore. I mean, this envelope is a lot smaller than the envelopes that we've seen in the previous figure. And the reason for this is, we'll take a look at the divergence to understand this, so we get this, so as I've said before, the convergent region of the CCKW is very important for triggering the convective processes. So this blue shading over here is the convergence, the negative divergence. And this comes just before this whole large precipitation envelope. But however, on the if you look ahead in time, we see that there's a region of divergence. And this is what suppresses the offshore propagation of the convective envelope on the day of the extreme precipitation. So the arrival of the CCKW interacts with the diurnal cycle in two ways. It amplifies it, but then it also suppresses it later on. So now we're going to examine a case study of a CCKW. So this is a CCKW that passed over Padang on the 21st of August, 2017. The figure on the left is the composite. So we've already seen the composite Hofmöller diagram. So this is a composite map of precipitation of the CCKWs at UTC 0-100 hours, so lag 0 in this case. And we're going to compare this to the snapshot of the anomalous precipitation rate on the 21st of August 2017 at UTC 0-100 hours. So they're essentially equivalent. And what we find is that there's a lot of similarities between the two figures. We get this aligning of the wind vectors at this time along the equator. So as I said, this is these are the westerlies from the CCKW coming in. You can also see them in the snapshot as well. And the wind vectors align with the coast. So this is the wind vectors, the wind approaching the Barisan Mountains, which run from the northwest to the southeast and aligning with the coast. And they also, we also get a large amount of precipitation beginning at Padang. The peak precipitation is around 5 UTC, that's very similar for this particular case study as well. So all in all, the composite and the snapshots are very similar. So this is really a nice archetypal example. Yes, there's more precipitation in the composite just because there's a lot more variability. There's a lot more data that's gone into this one. So yeah, just to drive home the point that it's a really nice example of a CCKW. And now looking at the Hofmöller diagram of this particular case study. So what we've got over here is the gray shading on this is the positive 10-meter zonal winds. The gray dotted contours are the negative 10-meter zonal winds. And the blue shading is, as before, the precipitation rate. And this magenta line is the trajectory of the CCKW that we've previously calculated. We've also got the observed precipitation rate in black and blue at the particular grid point of Padang. So what we see is that the CCKW initiates in the Indian Ocean and travels towards Padang around 10 degrees per day, which is typical speed for a convectively coupled Kelvin wave in the Indian Ocean. The day before, the 21st of August, so the 21st of August is our extreme precipitation day. The day before, we get this interaction with the diurnal cycle with the CCKW, as we've seen in the composites. And then on the day of extreme precipitation, the peak afternoon precipitation is around UTC 5 to 9, which again is what we found in the composites. And you can see that there's a clear westerly signal following the CCKW, and the precipitation lies at the region of convergence, as we'd expect. So what we want to do is understand how these CCKWs are represented in Met-UM forecasts. So this is Met Office Unified Model forecasts of the event, and see if we can find a way to better represent them. So the panel A over here is the 4.4 kilometer deterministic forecast. So this is a single ensemble member that was initialized on the 19th of August 2017. And this was the operational forecast used at the time. Importantly, its model boundary is at 90 east. And you can see, so outside of this, it's forced by the global model. So the boundary of the model is at 90 east over here. And I've marked on the trajectory just for comparison. And you can see that there's not really much of a precipitation signal following the CCKW trajectory. And you can also see this from the precipitation rate at Padang as well. So the black line is the observed precipitation rate, the blue line is the modeled. And at Padang, you don't get a peak of precipitation at all associated with the CCKW on this day. So all in all, this model isn't doing a great job. So what we did is we ran an ensemble of 8.8 kilometer forecasts. So this is lower resolution and initialized at the same time. And this was run by Stuart Webster at the Met Office. And we extended the western boundary out to 70 east. And you can see that the precipitation follows the trajectory. I mean, I should note that this is an ensemble, but all of the ensemble members showed some form of propagation of this CCKW. And we see this interaction with the diurnal cycle. And then we also see a peak of precipitation at Padang at the correct time. So extending the western boundary really was crucial for capturing the CCKW, its propagation, its speed, and interaction with the diurnal cycle. So finally, I just want to talk about the present work that I've been doing on equatorial Rossby waves. So this is sort of similar study on these Rossby waves, and we've chosen now to study their impact at Kuala Trengganu in Peninsular Malaysia. So this is this city that's on the east coast of Peninsular Malaysia. And this is a city that lies in the path of the northern convergent flank of a convectively coupled equatorial Rossby wave. So this experiences high Rossby wave activity that's associated with extreme precipitation. And we found, looking back on the database, that 20 equatorial Rossby waves coincided with extreme precipitation days over the period 1998 to 2020, which corresponds to 101% increase in chance of observing extreme precipitation given an equatorial Rossby wave is present. So I'm going to be repeating the similar analysis that I did with the CCKWs, studying equatorial Rossby waves at this location. So to summarize, CCKWs alter the diurnal cycle of precipitation at Padang by enhancing onshore rainfall on the extreme precipitation day and suppressing the offshore propagation of the diurnal cycle of convection in their wake. And CCKWs arriving in phase with the diurnal cycle are more likely to trigger extreme rainfall. We looked at a case study which demonstrates a clear CCKW signal even in the raw dynamical fields. And we found that in order to faithfully represent the CCKW and its interactions with the diurnal cycle, we needed to extend the standard operational domain out to 70 east to include most of the Indian Ocean, so that the initialization and the trajectory of the CCKW is captured in order to faithfully represent its interaction with the diurnal cycle. And the present work involves conducting similar analysis for studying the mechanisms through which equatorial Rossby waves trigger extreme rainfall at Trengganu. Thank you very much.
Thank you very much, Natasha. I think I've been a bit lenient with all our speakers. We've pushed a bit past 5:30, but they're fascinating talks, so I hope you'll bear with us. Do we have any questions for Natasha? I think Michael might have one online.
Yes, we've got a question from Satyavan Bioshi Ratna. Satyavan asks, how do the convectively coupled Kelvin waves interact with the Madden-Julian oscillation? And after that, he asks, in which season do the convectively coupled Kelvin waves, are they more prominent over Indonesia?
So there's no real, okay, I guess I'm answering the question backwards, but there's no real preferred time of arrival of the CCKWs. I did read in some other person's work that maybe in the summer it's more likely to trigger extreme rainfall, possibly to do with the fact that there's more extreme rainfall in that time. Sorry, I forgot the first question. Can you remind me?
Yeah, it's how do the CCKWs interact with the MJO?
So they are part of the subscale anatomy of the MJO. So often when you've got a convectively active phase of the MJO, we'll often see some CCKWs within it, but you can also, so this particular case study, it wasn't a active phase of the MJO. So they do exist in their own right as well. Yeah, you will get CCKWs and other types of equatorial waves coinciding with the MJO as well.
I think we should thank all three of our speakers from this excellent session. So thank you for joining us. Thank you for joining us online as well.